Hi, in this module we'll start talking about some of the more statistical aspects of the class. In particular, we're going to be talking about the general linear model, which is kind of the workhorse of the field. So what we're going to do is we're going to introduce kind of the basic concept behind the GLM in this module, and then in later modules we'll talk about refining it. So far in the data processing pipeline, we've talked about data acquisition and reconstruction, experimental design, and pre-processing. Now for the rest of the class we're going to be talking about data analysis, and this is the kind of statistical meat of the class. So there's multiple goals in the statistical analysis of fMRI data. And these include 1, localizing brain areas activated by the task, 2, determining networks corresponding to brain function, and 3, making predictions about psychological or disease states. To date, the most common use of fMRI has been to localize areas of the brain that activate in response to a certain task. And so in the little image here, we see that there's activation in 2 regions of the brain. And one is the visual cortex and the other is the motor cortex. And so what's happened in this experiment is that the subject had a light flash in his eyes, and then in response to this, pressed a button. So there should be activation in both the visual and motor regions. And this is what we see here. And these types of human brain mapping studies are necessary for the development of biomarkers and generally increasing our understanding of brain function. Typically, analysis is performed by constructing a separate model at each voxel of the brain. This is sometimes called the massive univariate approach. So basically what we do in the massive univariate approach is we treat each voxel as its own kind of entity and perform a statistical test on that voxel. Now this assumes an improbable independence between voxel pairs because, it seems very reasonable that 2 voxels adjacent to each other would behave in a similar fashion, especially compared to 2 voxels that are very far away in the brain. However, these dependencies are typically dealt with later on using random field theory, which makes some assumptions about the spatial dependencies between voxels. There are also other spatial models that incorporate relationships between voxels, but in the majority of cases, people use this massive univariate approach. The real driver in analyzing fMRI data is something called the general linear model. And so the general linear model, or GLM, approach treats the data as a linear combination of model functions and noise. And so the model functions are assumed to have a known shape, but the only thing that is unknown about them is their amplitude or their magnitude, and that's what needs to be estimated. The GLM framework is popular because it encompasses many of the commonly used techniques in fMRI data analysis and data analysis more generally. So to illustrate the general linear model, let's consider the following experiment. Let's consider that we have alternating blocks of finger tapping and rests. So this is kind of a paradigm where we tap our fingers for 20 seconds, and then we rest for 20 seconds. Tap our fingers for 20 seconds, then rest for 20 seconds, etc., etc., etc. Now what we're interested in doing is we want to construct a model to study data from a single voxel from a single subject. So now we don't have all this massive data, we're just looking at a single voxel, and we're looking at a time series extracted from that single voxel. Our goal here is to determine whether activation is higher during finger tapping compared with rest. Now one way of doing that would be to extract all the data that was acquired while we were finger tapping and put that in one compartment, and take all the data that was acquired while I was at rest and put that in another compartment, and then compare the means with one another. So this is what we see in the figure here. Now this is showing the fMRI bold signal measured during rest and versus finger tapping. Now if we want to determine whether or not activation is higher during finger tapping compared to rest, we could do something like a 2-sample t-test to see whether or not the means are significantly different. Alternatively, we could write it as a regression model, and this is beneficial for a number of reasons, and we'll talk about that as we go along. But in this, we consider the fMRI data strung out as a vector. So basically, on the left-hand side here, we have the fMRI data strung out as a time series. And so this is the time series from a single voxel of the brain. Now, we also say that this time series is a linear combination of 2 factors. One is a baseline, which is the intercept. And so that's just kind of the mean of the grand mean of under both conditions. And then we have a kind of a boxcar, which is the predicted task response. So we weigh the intercept by beta naught and the predicted task response by beta 1. And then we have residuals. Now, what is the equivalent of the t-test using this model? Well, the equivalent of the t-test would be to test the null hypothesis that beta 1 is equal to 0. If that's true, the boxcar disappears from the model, and the mean is the same regardless of whether you're finger tapping or resting. So in this case, the test of interest is that beta 1 is equal to 0, and this will give us an equivalent test to the t-test on the previous page. Now, this gives us an illustration of the format that we usually put a standard GLM model. So we usually write the GLM model as y equal to x beta plus epsilon, where epsilon is normally distributed with mean 0 and a variance-covariance matrix V. Now, if we go in and look at this, y is a vector of length n, where n is the number of scans that we have during our experiment. So in this case, y1 is the voxel measurement at time 1, y2 is the voxel measurement at time 2, all the way up to yn. So they're strung out there. So that's the fMRI data. The X is what we call the design matrix. That's where all the information about the task and whatnot goes into. So in this case, we have the first column is just a series of 1s, so that corresponds to the intercept. And the second column, in our example, that would be the boxcar, so it would be going up and down according to the experimental paradigm. And in the example on the previous page, p was equal to 1, so we only had this one regressor there. Now, the regression coefficients are the weighing of the columns of the design matrix. So beta naught is how much the slope is, and beta 1 would be the intercept, which corresponds to the predicted bold response. Now, the epsilon is a vector of noise. And again, V is the covariance matrix, whose format depends on whatever noise model that we use. So this is typically the model that we set up in analyzing fMRI data. Now, is this a good model? Well, the quality of the model depends on our choice of X and V. And so what determines whether or not this is going to be a good model is how well the design matrix captures what's going on in the data and how well V captures the noise structure. And in the model that we had in our illustration, that's probably not going to be a very good model because we didn't put very much thought into the design matrix or how to model the noise. So now that we have this model, now let's look at what are the knowns and the unknowns in this model. Well, Y is the fMRI data, so that's known to us. X is the design matrix, so that's user-defined. Beta are unknown regression coefficients, which capture the weight of all the columns of the design matrix, so that's unknown, it needs to be estimated. And also the components of V need to be estimated as well. So the unknowns here are beta and V. So how do we estimate these? Well, if epsilon is IID, so it's independent, identically distributed, then we can use something called ordinary least squares, or OLS, is the optimal estimate. So in this case, using this model, the optimal estimate for beta would be beta hat, which is equal to X transpose X inverse X transpose Y. So regression theory states that this is the optimal estimate of beta. And what's meant by optimal here? Well, this is what we call the best linear unbiased estimate. That means that in the class of all linear unbiased estimates, by unbiased we mean that on average beta hat will give us the correct results. And so in the class of all linear unbiased estimates, this is the one with the smallest variance. So we call it the best linear unbiased estimate, and so it's optimal in that sense. Now what happens if we don't have IID noise, and let's say that V is not equal to the identity in this case? Well, then the generalized least squares estimate, or the GLS estimate, is optimal in the same sense. And here we get beta hat is equal to X transpose V inverse X, and the inverse of all that, X transpose V inverse Y. So in this case, we have to incorporate V into our estimates. So now that we have a model, the GLM, and we have a way of estimating this, well, then it looks like we're in pretty good shape. However, the model that we just proposed has a number of shortcomings. And what we really want to do is we want to use our understanding of the signal noise properties of bold fMRI to aid us in constructing a better model. And this includes deciding on an appropriate design matrix as well as an appropriate noise model. So what are issues with the model that we just proposed? One is we know that the bold response have a delayed and dispersed form. So we have this hemodynamic response function. So the fact that I start finger tapping doesn't mean that my bold signal is going to immediately increase. Instead, it's going to take 5 to 6 seconds before that increase comes to fruition. Similarly, the moment I start resting, I still have heightened signal because of this hemodynamic delay. So just simply separating scans into these are scans that were taken while I was resting and these are scans that were taken while I was tapping my fingers won't be an appropriate way to model the hemodynamic response and the bold signal. So we have to incorporate this delayed and dispersed form of the bold response. Second, we already talked about that the fMRI signal includes substantial amounts of low frequency noise and drift, and so we have to take this into consideration in our model. Finally, we talked about that the data are serially correlated, and this needs to be considered whenever we're setting up a GLM model. So that's going to be the topic of the next couple of modules. What we really need to do here is we need to take this very simple model approach, this general linear model, and kind of refine it and make the design matrix and variance-covariance matrix fit to the data at hand. And so that's going to be the challenge. So setting up the GLM, formulating it and estimating it is pretty straightforward, but getting a good design matrix and a good variance-covariance matrix, that's what's challenging, and that's what we're going to talk about in the coming modules. Okay, so in this module we've talked about the general linear model, or the GLM approach, which is arguably the most dominant way to analyze fMRI data. In the coming modules we'll talk about how we can refine this model to make it fit the fMRI data a little bit better. Okay, I'll see you then. Bye.